Bună tuturor! Bine ați venit la unul dintre ultimele webinarii din etapa de pregătire de la UNbreakable, etapă de pregătire care se apropie de final. Mâine, pe 5 mai, începe concursul individual și sper că sunteți pregătiți pentru challenge-uri. Dar până atunci mai e puțin. Înainte totuși să trecem la prezentarea de astăzi, aș vrea să le mulțumesc tuturor celor care sprijină în acest an UNbreakable. Mă refer aici la Orange România, Bit Sentinel, CyberEdu, CCK România, Winsider, Seminars and Solutions și Zitec România, partenerii noștri instituționali, academici și media. Astăzi suntem alături de Alex și cumva trec direct la subiect pentru că e o personalitate destul de importantă pentru piața de cyber și pe plan național și internațional. Alex Ionescu este un renumit arhitect de securitate și un consultant expert pe sisteme de operare low-level, dezvoltare kernel, training de securitate și reverse engineering. El a făcut parte din echipa CrowdStrike în 2011. În calitate de membru fondator, a ocupat funcția de Chief Architect și VP of Engineering timp de 10 ani. Și în ultimele 2 decenii a depus un efort foarte mare în remedierea a zeci de vulnerabilități critice ale kernelului Windows. El este fondator al Winsider, Seminars and Solutions, o companie specializată în sisteme de operare low-level, inginerie inversă și training în domeniul securității pentru diverse instituții. Și astăzi vă va povesti câteva detalii despre The Future of Vulnerability Research. Alex, îți mulțumim tare mult pentru că ne-a acordat un pic din timpul tău și că ești alături de noi astăzi. O să te las pe tine să trăi din acest moment.
Mulțumesc foarte mult! Prezentarea o să o fac în engleză, doar pentru că majoritatea materialului și cuvintelor vor fi în engleză, dar la sfârșit, dacă sunt întrebări, sunt fericit să răspund în limba română fără nicio problemă. Ok, o să încep screen share-ul. Ok. Deci, pe webinarul ăsta, I'm going to talk about the future of vulnerability research. I'm going to focus specifically on Windows vulnerability research, but a lot of the topics and concepts can be generalized and will likely make their way into other operating system platforms as well. So just a little bit about myself. As was mentioned, I've got a 25-year-long career in Windows and operating system research, training, development. I've written the Windows Internals book series for the last 3 editions. I was previously at Apple on the Core OS team, responsible for porting macOS to ARM. And I was also on the founding team at CrowdStrike, which if you're following cybersecurity, most of you are probably familiar with, as one of the top security vendors these days. Currently, I'm Director of Platform Operations and Research at CSC, which is the Canadian Security Establishment. It's essentially the Canadian version of the NSA in Canada, essentially. So I've been given over my career, been giving talks and presentations and blog articles. I kind of officially retired, so to speak, from the public space in 2019. I gave my last official keynote at OffensiveCon in Berlin, but I still enjoy, whenever I can, giving little talks for smaller, more impactful conferences and competitions, and UNbreakable, I think, is one of those events. So I think you're in a very unique position if you're doing cybersecurity, if you're doing vulnerability research, if you're doing operating system development, or just normal programming, honestly, because the next 5 or so years are going to be quite interesting, and I think present some pretty fundamental paradigm shifts in computing. Why is that? Well, I think for the first time in a really, really long time, there's finally a really strong push towards operating system security. Different than the operating system providing the basics and then users being expected to install security software, most of the major OS vendors are now making sure that the operating system comes built in with security. An analogy that I've always given is that the OS world so far has been like car manufacturers giving you a Toyota, a Honda, a Lada, a Dacia with no seat belts, and then you have to go install seat belts from one of 50 different seatbelt vendors. Obviously, no, that would be illegal, right? Nobody makes cars that way. Maybe the Ladas, but in computers, that's kind of how it is, right? You install Windows, and if you connect Windows XP to the internet, if some of you were unlucky enough to use that, within about 30 seconds of connecting a Windows XP system to the internet, it's not your system anymore, right? That's kind of crazy. If you connect the Windows 11 system to the internet, you're okay. Even if you have no firewall, even if you don't have the latest patches installed, you're probably not going to get owned in the next 3 minutes. And there's a number of reasons for that. On the Windows side, one of the things that's really been driving Windows 10 and Windows 11 security is this idea of signing. So you now have in Windows 11 this built-in feature that only applications that are signed are going to launch. It's called Smart App Control. This means that malware, ransomware, if it's not signed, it's not going to run. If the binary does not have reputation, it's not going to execute. This is similar to macOS's gatekeeper feature, but even on macOS, that feature is not on by default. And if you right-click open, it opens anyway. With Windows 11 on a clean install, the Smart App Control is probably one of the most fundamental compatibility breaking changes in Windows history. Right now, it's not enabled by default on a non-clean install, so it has to be a clean install. But once it kicks on, it basically means that if the application is not signed, it's not gonna launch. Now, obviously, malware developers can sign their applications, but once you're signed, a signature can be revoked, right? And that can be done in a matter of minutes. So really enforcing this level of signing is pretty fundamental. And Windows already has driver signing as well for code that loads in the kernel that's more privileged. With Windows 11, the hypervisor is now used to enforce driver signing by default on clean installs. And then at the firmware level, we have something called Secure Boot that is now enforced on by default on all computers. So this is really the first time that we have firmware signing, driver signing, application signing all on by default, which has never been the case before. And that offers a pretty big compatibility cost, but done in the name of security. Another example where things have changed quite a bit is memory safety. You've probably heard about Rust and other memory safe languages. Rust is kind of a darling child for operating system development because it doesn't have a runtime. It compiles into very easy to read, very simple native code. So it's kind of designed for systems programming. Windows is changing parts of its own code to be in Rust. The font parsing now, called Direct Write Core, is written in Rust. Parts of the kernel are now being ported to Rust, even system calls. And even outside of Rust, more modern versions of the C++ runtime, the GSL, which is the generic spanning library, is being increased. So Microsoft is also making fundamental efforts into making the code safer. Credential theft is a big problem where passwords are being stolen from Windows processes that store credential information, LSAS being one of them. That's the Windows service that stores your passwords, your domain secrets, and so on and so forth. This now runs in Windows 11 under what's called Protected Process Lite, or PPL, which makes it much harder for an attacker to go inside. For biometric logon, Windows now supports that through what they call Windows Hello. So instead of using your password, you can now use your face, you can now use your finger, or other types of biometric authentications. And these are now protected by the hypervisor under what's called Secure Biometrics. And even the way hashes are stored, there's a very famous hashing protocol called NTLM that Windows uses that's being deprecated in favor of Kerberos everywhere. So again, big efforts into really 2-3 decades of issues with how credentials are being stored and manipulated that are also being fixed. Persistence. Malware always likes to persist on a system to make sure that it comes back. In a normal Windows system, your C drive, you have your programs there, you have your data, you have your documents, you have Windows, everything is together without any separation whatsoever. So if you get ransomware, it can encrypt your documents, it can overwrite your files. If you get a bad Windows update, it can also overwrite your applications. If you get a bad application, it can overwrite your system. macOS moved away from this, right? On macOS, you have something called SIP, System Integrity Protection, which means that even if you're root, even if you're the administrator, you cannot modify system binaries. And vice versa, applications cannot access your documents without your permission. Windows had a version called Windows 10X where they implemented this under what they called state separation. Windows 10X unfortunately never shipped, but there are now rumors that Windows 12, which is called Hudson Valley, will support state separation, meaning that you're going to have 6 partitions on your drive, one with your OS, one with your OS updates, one with your programs, one with your applications, one with your temporary files. And that means that it's a lot harder for malware to persist. It means it's a lot harder for you to accidentally corrupt the operating system. It's a lot harder for the operating system to accidentally corrupt your data. And again, big paradigm shift into making desktop and server systems function more like phones, function more like Xboxes than in the past. And then there are a number of exploit mitigations, which, we don't have 10 hours here, but everything that you see on your slides, you can Google for. These are all different mitigations that Microsoft has added to make it a lot harder that if you do have an exploit, if you do have a memory corruption, if you do have a vulnerability, you're gonna have to do a lot of work to actually weaponize that exploit into making it do something useful on the machine. Because you have to understand, obviously, if you find a bug, if you find a vulnerability, that's just step one. Finding a way to make use of that vulnerability, to leak information, to execute arbitrary code, to elevate your privileges, that is a whole other step in the process. And you can argue that if there is a bug and there's no way to actually weaponize it, there's no way to actually make the bug useful to an attacker, it's a low priority bug, right? There's many other kinds of bugs we should go fixing instead of ones that, yes, are vulnerabilities, but they're vulnerabilities that nobody can do anything about. And so these are all really in the last 2-3 years, changes that we've seen, right? Almost as fundamental as when drive encryption was being added for the first time to Windows and Mac OS and Linux, almost as fundamental as when firewalls were being added for the first time in Windows XP. We now have another kind of paradigm shift, another evolution of OS security that is happening. And now not just 1 or 2 things, but 8 or 9 things all happening together at the same time. And the operating system is one important part of what's running on your computer, but then you have what's called below the operating system as well, right? Your firmware. And there's been a number of firmware vulnerabilities, issues in what's called UEFI, the Unified Extended Firmware Interface, issues in what's called SMM, the System Management Mode, and Microsoft and the industry have added lots of mitigations to UEFI, to SMM, as well as the concept of signing, as well as the concept of using Trusted Platform Module or TPM. With Trusted Platform Module, you can now measure and essentially attest the boot chain, making sure that not only you're loading signed binaries, but that also the binaries that you're loading are the ones that users are expecting to see. And that is another important part of making sure that we really understand what is executing on the computer. There's also attacks that can be done through remote hardware, what's called DMA, direct memory access. This allows somebody to plug in a specific piece of hardware in your machine and attack the kernel, attack physical memory. A number of hardware components such as the IOMMU, a number of hardware features such as total memory encryption now make this significantly harder or impossible. And with upcoming technologies like Intel TDX and AMD EVSNP, virtual machines running on hardware can actually now be protected from the hardware itself. So that means if you have a VM in the cloud or a virtual machine on your system and your system is compromised or the cloud is compromised, the data in the virtual machine is still encrypted and is still protected. Again, these are all big shifts in security that we had not seen for the last couple of decades. Outside of kind of Windows itself, there are a number of other industry-wide changes that are important to talk about. One of them is what's called Cherry. And Cherry is a project out of the UK, which is funded by the US as well, which now can boot BSD. It can soon boot Linux. Maybe one day it can boot Windows. And the fundamental idea behind Cherry is to replace the idea of pointers with essentially 128-bit memory reference identifiers. This means that you're no longer dereferencing a pointer to access things in memory, that every memory access is now a signed, codified, protocolized memory access specific to some byte that is interesting to you. So people cannot just access random bytes of memory whenever they want to. And even the access mechanism is encoded in there. So if somebody has a reference tag that gets them, lets them do a read, they cannot reuse that to do a write. That is a different signed reference identifier. So every memory access becomes a transaction essentially that is access controlled. This is the most fundamental change in computers in 50 years. The performance of this is obviously not where today's computers are. There is a big performance hit to making every memory transaction, every memory access a complicated access control transaction. However, there is a lot of effort being put into lowering that memory overhead. And maybe one day when we get it down to 10%, 5%, whatever the number is, the industry will decide, you know what, in exchange for no longer having any memory corruption vulnerability, we're willing to lose 10% performance. We don't necessarily have to go all the way to Cherry. I mean, ARM64 is another platform architecture, hardware architecture. Some of you probably have, I mean, all of you probably have phones that are ARM64 phones. The M1 and M2 Apple Macs are based on ARM64, and even Microsoft Surface Pro now has ARM64 machines. Now, ARM64 used to mean that you had to recompile your binaries, but Microsoft and Apple now have emulation technologies. Microsoft has one called XT-JIT2, which basically means you can launch any 32-bit, any 64-bit binary natively on ARM64 with almost no performance loss. And they've all supported, of course, things like .NET, OpenCL, IIS, Hyper-V. You can buy ARM64 Surface Pro and essentially get double the battery life, almost the same performance as an Intel machine, and a much more secure platform. You can have less exploits, less malicious code, less stuff that exists for ARM64. And ARM64 has technologies like pointer signing, which isn't quite the same thing as Cherry's memory tags, but it does make exploitation a lot harder. If you've been paying attention to the news, you might have seen the US making a lot of noise about what they call SBOM, software bill of materials, which is all part of the software supply chain validation that's being done kind of as a result of what happened with SolarWinds. So a lot of governments, a lot of industries, a lot of academics are now trying to get a better understanding of what code is running in a binary, what libraries are being used, what dependencies were taken. And kind of one final industry-wide change is this idea toward running less code on your machine. You know, in Windows, for example, you have what's called Application Guard, where you can open a web browser in its own virtual machine, where you can open an Office document in its own virtual machine. Cloudflare, I think, now has a feature where you can browse a website on their servers. And I think you're going to see a lot more movement toward distributed computing, where kind of even like Google Stadia, where you can play a game on Google's cloud, where less workloads are running on your system, more workloads are running on somebody else's system. And for cases that are not performance, where performance is not critical, this again means that the security of your computer not only has increased, but if there are issues or compromises on your computer, there's less things that can go wrong, essentially. So this is kind of an industry and code aspect of how things are changing. There's also companies changing. For example, Microsoft has made pretty significant changes in terms of how they operate themselves. MSRC, which is the organization of Microsoft that's in charge of receiving security reports and fixing them, now has a team called Morse. And as part of Morse, when they get a security vulnerability, instead of just fixing that vulnerability, they are now looking at variants and writing fuzzers to understand other types of those vulnerabilities. That's something they've never done before, which I actually used to give keynotes on how that was a bad thing for them not to do. They now do that, and that means that they're fixing dozens more vulnerabilities every year than they used to. They also work a lot more with open source projects. So they're engaged with Google on ASAN, which is the address sanitizer. They now have their own Microsoft kernel address sanitizer. They're working with Syscaller to validate their syscalls. They're working with other open source security projects AFL, American Fuzzy Lop, to leverage what others have built to find, again, vulnerabilities faster. And they're engaged with AMD, with ARM, with Intel on their open source projects as well. And then finally, they're all more open to documentation. So the documentation is clear now. They do more open designs, more open specifications, which means that it's easier to find issues and have the conversation earlier in the design stage with Microsoft. So all of these things all together essentially mean that computer security on Windows and in the industry as a whole is getting a lot better. And it's a lot harder in theory to find vulnerabilities and, even more importantly, to exploit those vulnerabilities. But that's not necessarily going to be the case for the next few years. And here's why I think that is. One thing that Microsoft does really well is that they dog food their operating system. So that means that every new release of the operating system, every new internal weekly build, they try on their own employees. And dogfooding is usually a pretty good thing to do because it means that you can find issues a lot quicker in the operating system. However, it also means that your entire company is always living on the bleeding edge. That means you have a sense of security that is much higher than everybody else because most of you probably don't have all the mitigations turned on. You're not all running Windows 11 on clean installs. So while Windows has those features and those capabilities that make you much safer, we're not at the stage yet where everybody has those things enabled and where everybody's running on Windows 11. But at Microsoft, they are. So that means the world they live in is basically 5 years in the future from where we're likely going to be living in. That means that it can create a false sense of understanding of what today's problems are versus the fact that, yeah, they might not be problems anymore in 5 years. It also means that, as you're moving towards languages, runtimes, and operating systems that have more security guarantees, you're likely to write code with a little bit less thought, essentially, right? If you know that it's impossible on a cherry system for memory corruption to affect code execution, then maybe you're going to be a little bit less careful with memory corruption, because what's the worst that could happen with a memory corruption vulnerability? Your program is going to crash. That's still a problem, but you're not going to get arbitrary code execution anymore. So likely over time, your code quality might suffer, which ultimately won't impact the security. That's true, because now there's all these guardrails around it. But it does mean that if the guardrails are not there, if the code is executing on a legacy system, now you have a problem, right? Because you're essentially writing unsafe code that's relying on a safe environment. It also means that as you're learning a new language, right, you might be making more mistakes. We've been writing C and C++ code for 2-3 decades now. We've only been writing Rust code for maybe 5 years at most. If somebody started Rust a long time ago, there's more people need to understand about Rust in order to safely use it. There's ways to write vulnerabilities in Rust as well. Design level logic flaws exist in any language. And so what ends up happening is that code is likely going to be suffering a little bit in immediate quality as it's written. And it also means that code reviews are probably going to be less thorough, because there's going to be more assumptions that, oh, don't worry about this, the runtime makes sure that it's going to happen. I saw this in some of my old work where in Windows, when you access an object, you must create a handle. And when you're done accessing the object, you must close the handle. Now, if you use C++ with REII, you can use template classes and generics to essentially make handles smart so that when they're no longer referenced, the handle's automatically closed. And you put it in the right code in the backend to make that happen. So during code reviews in the first few years, people still said, hey, you forgot to close the handle. Hey, you forgot to close the handle. And developers would say, no, don't worry. This is a new scoped handle. I'm using RAII, the handle's being closed on its own. And after 2, 3, 4 years, people stopped looking for, did you close the handle? Because they're like, oh yeah, scoped handles, they're closed automatically. But guess what happens when somebody now writes code that doesn't use a scoped handle, right? That uses some object that does not have a template added behind it yet, or where there's more complicated access patterns where the handle is not automatically closed. Now people are no longer thinking about looking for handles being closed or not, because they end up in this world where, oh yes, the handles are always closed. So this is what can happen when you have a language that's too safe, is that people stop thinking because they trust the language, which is not a bad thing. I mean, at the end of the day, these safety features are there so that we can think more about design, so we can think about more about performance. But that shouldn't come at a cost of completely closing our eyes on security. So my thesis is essentially that because of all of these mitigations and features that are being added, code that executes in these environments is going to be running in a much safer environment. In the future, where the entire planet, so to speak, all Windows users are running in this environment, that's great. But in today's environment, where we're not quite there yet, that's a problem. The problem is because code is being written today and it's shipping today. Code is not shipping 5 years from now. And it's being written as if it is going to be running 5 years from now, because today at Microsoft and at other large companies, people do have the latest and greatest hardware. They do have the latest and greatest operating system. And there's a mismatch between global reality, code being written for future reality, and yet still shipping in today's global reality. So that means that likely bugs that are found now and identified are going to be deprioritized if all these mitigations make the bug impossible to exploit. But if only 1% of people are running those mitigations turned on, until that 1% becomes 100%, that is still a vulnerability that needs to get fixed. But if you're running an engineering team, well, obviously you might prioritize fixing the bugs that are still exploitable 5 years from now, right? There's still going to be design level issues. There's still going to be fundamental flaws that are going to be issues 5 years from now too. Those are going to get prioritized, which is fine. But how much you deprioritize the other bugs can be a problem. And we've seen this before, actually. This is not a crazy theory. Microsoft, Linux, Apple all fixed null pointer dereferences in the operating systems about 8-9 years ago. So as of Windows 7, you could no longer allocate the null pointer, address 0. With macOS Leopard, I think, you could no longer allocate the null pointer. And Linux also prevented in 3.16, I think, allocating a null pointer. That meant that if you had a null pointer dereference, an application would crash. Before, you could actually get a way to allocate a null pointer and make a null pointer dereference become an arbitrary read, which could then lead to an arbitrary write or even arbitrary code execution. And so null pointer dereference bugs are no longer fixed by Microsoft. If you submit a null pointer deref, unless it's in the cloud, where you can get the entire, you can get Azure to crash, which is a DOS attack, those bugs typically get deprioritized so low, they don't get fixed at all anymore. Now, what happened a few years ago? Microsoft added support for something called enclaves in the operating system. As part of adding support for that, they had a design flaw, and it allowed you to allocate null again. Now, a researcher eventually found this, and the bug was eventually fixed about 9 months later. But during those 9 months, or that researcher would have never submitted that vulnerability, null pointer dereferences became arbitrary code execution again, or arbitrary writes. So that entire backlog of bugs that weren't fixed anymore because they didn't matter, suddenly mattered again. Now, thankfully, this was a 9-month window. Microsoft was told about the bug and they fixed it. But you could imagine how maybe this bug would not have been found for 5 years or 10 years or ever, who knows? So that's why it's important to balance. Am I saying that Microsoft should be fixing all null pointer derefs? No, because there's bigger bugs out there. But it doesn't mean that when you take dependencies on things no longer being possible, you got to make sure they're actually no longer possible. So today, I think we're likely going to be seeing more raw bugs being written. So actually, ironically, more buggy code, but less exploitable code in the future. But until the future comes, we're going to have more buggy code and it's going to be just as exploitable as before. So I actually think we're going to be seeing, we'll see if I'm right or not, over the next 5 years or so, more exploited vulnerabilities in at least Windows code, because there'll be more assumptions made by Microsoft developers around the exploitability of those bugs or not. And researchers also, if you're reading this, if you're paying attention, you're realizing, oh, all these issues that I found, if Alex is right, and the whole world runs Windows 11 2 years from now, with all these mitigations turned on, my bugs are no longer exploitable. If I'm selling bugs or releasing bugs or doing whatever, I better do it now before the future comes. So I think we'll see an interesting kind of short-term peak in exploitation, and then a much, much lower level than before, right? So we're here now. I think we'll go up here for a little bit, and we'll go down where we want to be going. That's essentially my thesis. And that's something I think you need to be careful of, even in your own future jobs, even in your own research. It's great that we have all of this hardware and software and runtime security that's being added, but until it's available for everyone and until it's running everywhere, keep in mind that your memory safe code might not be memory safe on somebody else's system for the time being. So we'll see if my warning comes true. Now I sound like one of those old people that's scared about new technology. Hopefully that's not how I come across, but that is the message that I wanted to relay to you today. Fairly short presentation, but hopefully meaningful, and you have the slides as well to reference any of these. I know I threw a bunch of acronyms, a bunch of code names, a bunch of technologies at you. The goal is also to get you to research some of this stuff on your own and see what you think of it, and potentially bring some of these improvements to other operating systems and other platforms as well. So with that, I'll stop here and I'll see if there's any questions from the audience.
Avem trei întrebări, în zona de Q&A. Dacă e ok și cu tine, o să le citesc pe rând. O citesc pe prima mai întâi. Ținând cont că Windows-ul este un sistem destul de closed source, cum ai reușit să obții informații și să ajungi să faci exploitări pe kernel/mitigate protecții specifice sistemului de operare Windows? Pentru că tot am căutat informații, dar nu prea am găsit. Cele mai cunoscute ar fi Fuzzy Security și Curl Encoder, din ce am găsit, dar deja sunt outdated.
Da, deci Windows este un sistem closed source. Există diferite feluri de a penetra, a înțelege ce se întâmplă cu sistemul. Unul dintre metodele astea este, bineînțeles, să citim cărți ca Windows Internals, care am scris-o eu și alții, ca bloguri. Cum persoanele astea, cum eu am putut să descoperi chestia asta, este cu reverse engineering. Deci Microsoft, chiar dacă nu pun codul online, există ce se numesc public symbols sau fișiere PDB. Fișierele astea conțin numelor de funcții care există în fiecare fișier, deci în kernel, în drivers, în aplicații, și conțin și structurile de date care există, diferent, structura de proces, structura de thread, combinând un utilitar ca IDA Pro, ca Hextrace, ca Ghidra, ca Binary Ninja, care sunt utilitare de reverse engineering, cu symbol files care sunt date la Microsoft, poți să analizezi fișierul executabil ca kernel.exe, de exemplu, și să vezi ce funcții există și să vezi ca un pseudocod C, să vezi ce se întâmplă înăuntru și și de data structures, să vezi ce field-uri sunt accesate, și cu asta poți să înțelegi mult mai deep ce se întâmplă în codul ăsta. Deci așa se face, după aceea scrii niște bloguri, punem niște cărți, facem niște slide-uri, alți verifică și văd ce văd și ei, și așa se continuă. În alte cazuri, Microsoft fac ei bloguri care explică cum funcționează unele chestii și unele cazuri chiar există cod. În câteva cazuri rare, Microsoft a început să pună open source câteva mitigații care pune.
Ok. Următoarea întrebare sună cam așa. Ce le recomanda celor care vor să activeze pe această ramură de exploit development și cam ce cunoștințe și skill-uri sunt necesare pe partea de reverse engineering?
Deci, o parte, cred că este din ce am răspuns deja, de a analiza, de a înțelege cu reverse-ul, cu symbols-uri, cu bloguri, cu cărți. Altă parte este, există cursuri și traininguri online de bază despre exploit dev pe Windows. Puțin cam outdated comparând cum a ajuns Windows 11, dar te învață oricum chestiile de bază, cum să faci un heap grooming, cum să masajezi memoria, să fie pointerul unde vrei să fie, cum să bypassezi protecțiile de genul no execute, cum să bypassăm address space load randomization, ASLR, cum să faci rope chains. Deci pe internet există diverse tutorials și există și câteva online trainings. Costă câteva sute de dolari, nu mii, și multe companii te vor plăti pentru chestiile astea și există multe conferințe unde se dau trainingsuri puțin mai scumpe, deci de obicei, dar ca studenți de multe ori sunt multe discounturi disponibile și să începi să scrii niște exploatări pentru asta. Cea mai ușoară, cea mai bună pentru mine metoda este să scrii o mică aplicație, să scrii un cod al tău și după aceea să încerci să-ți exploatezi propriul tău cod. Și există și pe internet, de exemplu, un driver care se numește Extremely Vulnerable Driver, care a fost creat de cineva pentru tutorials cum să-l exploitezi.
Ok. Următoarea întrebare venea cam din aceeași zonă. What tips do you have for someone who likes low-level things, kernels, OS internals, bootloaders, and is looking forward to doing vulnerability research in this area?
Da, cred că acest răspuns până acum și am văzut că întreba și what about bug bounty in this field. Există programe de bug bounty. Microsoft, de exemplu, are un bug bounty cu MSRC. Mai targetat pe hypervisor, pe browser, deci e un bug bounty mai dificil. Dar au și un general bug bounty pe Windows Insider Preview. Deci dacă downloadezi versiunile beta de Windows, care sunt gratuite, pentru un info-leak cred că dau $5, pentru un privilege escalation vreo 3.000 și dacă ai un remote vreo $10.000 americani, deci not bad. Și cu alte companii au și ei bug bounty programe de ale lor, Background, de exemplu. Și este un fel foarte bine de a începe de a face reverse și exploit dev. Altă posibilitate este, bineînțeles, să nu sărim imediat la kernelul lui Windows sau la aplicațiile Microsoft, dar aplicații care rulează pe sistem sau la driveruri scrise de alții, driveruri de video, de grafică, de rețele. Există multe vulnerabilități în driverurile astea, care persoanele care lucrează la companiile astea nu scriu necesar cod la același calitate ca Microsoft și te învață oricum niște tehnici de exploit și de Windows Dev, dar la o bară la un nivel mai jos, mai ușor pentru început.
Ok. Mai așteptăm câteva momente să vedem dacă vor mai fi întrebări din partea celor prezenți. Între timp o să profit eu de ocazie să le transmit că la competiția pe echipe vor avea un exercițiu din partea ta pe care am văzut că l-ai pregătit și îl vom urca în timp necesar ca să fie disponibil în perioada 19-21 mai, când va fi și competiția pe echipe. Tips and tricks pentru acel exercițiu sau...
Cred că e un exercițiu care are multe feluri de a-l solva, de a-l descoperi răspunsul. Analiza statică va fi importantă, să fie reversat în Ghidra sau IDA sau alt tools, dar ce am vrut să fac cu exercițiul ăsta este și să arăt importanța analizei dinamice. Deci să se execute codul într-un debugger și să vadă ce face. Ambele două sunt importante și are tot felul de mix Windows internals tips înăuntru. Deci vor fi multe chestii care dacă le-ți înțelege, vă ajuta în viitor cu analiza de malware și cu analiza de sistemul Windows. Deci poate să fie foarte simplu și foarte greu în același timp, depinde de cum va fi făcută analiza.
Ok. Văd că nu mai vin alte întrebări. În acest caz, Ba da. Credeți că lumea se mută pe ARM? Știu că este folosită peste tot în jurul nostru deja, de la Raspberry Pi, telefoane, rutere, televizoare IoT, dar ce credeți despre desktops și laptops?
Da, deci personal cred și sper că da. Apple deja s-a mutat 100% pe ARM. Amazon AWS și Azure acum pe cloud au sisteme serveruri ARM unde avem aproape aceeași performanțe ca Intel sau AMD, dar cu mult mai puțină putere. Și asta e ce e interesant cu ARM, că pe un laptop înseamnă mai multă baterie, mai mult timp de utilizare, dar în cloud înseamnă mai puțin electricitate, care înseamnă mai puțin cost, mai puțin cooling, mai puțin heating, electricity cost. Deci este o eficiență foarte interesantă și da, ce lipsește este desktop-ul Windows. Avem acum laptopul Windows, cum a spus Surface, face una, Lenovo are un ARM și Windows a scos vara trecută Project Volterra, care e un ARM64 desktop, arată ca un mini Apple. L-au releasat pentru, cred că, $700 americani pentru dev și este primul desktop Microsoft ARM, nici nu are ventilator, are no fans și are 8 core-uri ARM64. Cred că lumea se va muta acolo pentru majoritatea utilizatorilor de computere. Acum, video editing, cred că încă are și gaming, cred că va rămâne sisteme Intel sau AMD, dar cred că pentru majoritatea de office use sau school use sau cloud workloads va fi un mare push spre ARM, cum vedem la Apple. Apple e 100% ARM acum și următorul Mac Pro va fi și el pe ARM, deci cred și sper că se va întâmpla această mutare.
Ok. Încă două. Există similarități între sistemele de operare pe partea de internals și dacă da sau nu, cum ar trebui să abordăm acest caz?
Există foarte multe similarități. Majoritatea, de exemplu Windows NT, cum se numește, a fost bazat pe baza de VMS, care executa în anii 70 și 80 pe sisteme PDP-11, putem să întâlnim pe părinții noștri cum erau alea, cu punch cards-uri. Și dacă cumpărați un Open VMS Internals Book din 1988, o să vedeți termeni de genul paged pool, interrupt request level, APC, care sunt aceleași termeni care există încă Windows 11. Linux, bineînțeles, și BSD bazate pe Unix, care și el a avut bază pe VMS, deci foarte multe idei de bază, access control list, threading, scheduling, memory management, heap, sunt foarte similare între cele trei sisteme de operare. Implementarea câteodată este diferită, bineînțeles structurile de date sunt diferite, dar dacă cineva înțelege, de exemplu ceva ca mine care este un expert în Windows internals, am putut să scriu macOS kernel code și înțeleg și Linux-ul cum merge. Deci abordarea cazului este că înțelegi un sistem extrem de bine, celelalte o să realizezi, asta e scheduling-ul, asta ok, este interrupt management-ul. Pentru că multe dintre sistemele sunt bazate pe aceeași istorie din anii 70 și la sfârșit tot rulează pe același Intel sau ARM. Deci când vrei să configurezi o întrerupere, nu există 15 feluri cum se configurează chestia asta, citești manualul Intel și îl faci cum spune Intel.
Ok, și cealaltă întrebare. Mac Pro at Worldwide Developers Conference 2023.
Întrebarea asta se numește Fishing for Rumors, deci I decline.
Acceptăm. Mai așteptăm tot așa câteva momente în cazul în care mai durează un pic să scrie cineva vreo întrebare. Care este diferența dintre AMD și Intel ca și sintaxă și cât de greu este un exploit pe cele două arhitecturi?
Între AMD și Intel nu este aproape nicio diferență la nivel de sintaxe, pentru că amândouă sunt arhitecturi x86, x64, deci instrucțiunile de bază sunt identice și funcționarea este identică. Există o diferență când vorbim despre virtualization. Deci, AMD are tehnologie de virtualizare diferită de Intel. Intel se numește VMX și AMD a numit-o altfel, am uitat, sau VTX și VMX. Deci, instrucțiunile de virtualizare și exploiturile la nivelul de hypervisor sunt diferite între AMD și Intel și câteodată fiecare au extensii diferite. De exemplu, Intel are acum niște instrucțiuni de calcul pe matrici specializate care nu există încă pe AMD. Dar la nivelul de exploit dev, nu cred că am văzut decât în câteva cazuri rare unde AMD sau Intel făceau diferență. Bineînțeles, pe ARM, care este complet o arhitectură diferită, instrucțiunile sunt complet diferite și totul e diferit. Deci pe ARM, bineînțeles, exploiturile sunt 100% diferite în assembly cum arată. De aceea, de multe ori, recomand lumea să se uite nu la exploituri care au nevoie de instrucțiuni în assembly code, dar la design level sau logic level vulnerabilities, care sunt probleme de implementare în C, în C++, în Rust. Nu contează dacă nu verifici, dacă userul poate să scrie pe un fișier, nu contează dacă ești pe Intel sau ARM64, lipsește un access check în zona aia. Deci, greutatea a găsi un exploit depinde de ce fel de exploit căutăm, unul de design sau unul de corupție de memorie și foarte rar depinde de arhitectură sau de compania care a făcut arhitectura.
În regulă. Ultima întrebare care apare aici. Ce este greu pentru mutarea gamingului pe ARM?
Cred că cea mai greu de se muta pe ARM este pentru că nu există încă cărți grafice Nvidia sau AMD pe ARM. ARM are cartea lui, tehnologia de carte grafică, care e foarte bună pe un telefon. Există un gaming de telefon de la Apple cu multă calitate, dar nu avem un Nvidia RTX 4080 compatibil cu ARM. Nu avem încă the bus bandwidth PCI Express 4.0 pe ARM. Deci capabilitatea să mutăm texturi imense de câțiva giga direct de pe CPU pe carte grafică la rezoluții 4K, 8K, 144 de Hz. Nu suntem încă acolo pe sistemele ARM și nici rendering tools și graphic tools care există compania de creație de joc. Nu sunt necesar probleme tehnice, doar că nu s-au făcut investiții să avem arhitectură de bus și cărți grafice în domeniile astea și Nvidia și, bineînțeles, AMD nu vor care a cumpărat Radeon. Nu știu dacă AMD o să facă cărți pentru ARM, că bineînțeles vor canibaliza propriul lor arhitectură x64 și Nvidia e un mare efort să facem cărți grafice pentru alt tip de bus sau pentru ARM să incorporeze PCI Express. Deci asta e mare dificultate care o văd în capul meu.
Mulțumim tare mult pentru răspuns și mulțumesc și lui Cristian pentru multele întrebări și pentru implicare. Mai așteptăm dacă să mai avem câteva minute până la finalul acestui webinar.
Cristian, de fapt, a fost plătit să întrebe întrebări bune, nu?
Chiar nu. Dar îi apreciem foarte mult proactivitatea. Ok. Mulțumim și noi, Cristi, din nou. Dacă nu mai sunt întrebări, Alex, mulțumim tare mult pentru prezentarea și prezența ta de astăzi. Te mai așteptăm cu mare drag și la ediții viitoare, pentru că sigur vor mai fi și insight-urile tale vor fi valoroase pe viitor. Rămâne să ținem legătura și cu participanții mă întâlnesc în aproape un sfert de oră, în 20 de minute, la următorul webinar, susținut de un expert în comunicare de data aceasta. Până atunci vom face o scurtă pauză și, Alex, ție-ți urez o seară minunată și ne auzim. Mulțumim tare!
Mulțumesc mult! Mersi pentru invitație! La revedere!